Okay, welcome back. So we'll continue with our discussion on compound semiconductor. I told you about the introduction of compound semiconductor in the last class. We had discussed the different kinds and categories of some compound semiconductor, and some of the uses we had touched upon, like wide LED emitter, detector, and so on. There are a lot of wide applications. We'll come to know them one by one here. I told you in today's class we shall discuss three things. One is Vegar's law, one is epitaxy and mismatch, and one is heterostructure. We'll touch them only briefly, not go very deep, because each of these topic is very profound. We shall understand as much as is required to understand the devices made of compound semiconductor. Okay. I told you that you can mix and match different types of compound semiconductor and alloy them to tune the band gap, to tune the properties of the material. That kind of flexibility is not there in silicon, for example, or germanium. You can mix silicon germanium, by the way, then that also gives you limited opportunities there. Anyways, the first thing we have to understand is Vegar's law. What is Vegar's law and why this law becomes important? That is actually important when you try to understand alloys of material, like you are taking gallium arsenide, you are taking aluminum arsenide, you are mixing them in some ratio 50-50, 40-60, 20-80, whatever, and you have aluminum gallium arsenide, then the material properties can be predicted fairly accurately or close to accuracy using Vegar's law. So let's come to whiteboard today, and we'll see that you have Vegar's law. Vegar's law, what does it Vegar's law? You will see it very quickly actually. Suppose you have a gallium arsenide, and gallium arsenide has a lattice constant A, okay, A gallium arsenide, I will call it X again. So what I will do is that A gallium arsenide is the lattice constant of gallium arsenide. Maybe it may be 5 angstrom, it may be 6 angstrom, I do not remember the exact value, but it may be few angstroms, okay. Its gallium arsenide has a lattice constant. Now I have aluminum arsenide, and aluminum arsenide, of course this band gap is 1.4 eV and this band gap is around 2.2 eV. Suppose aluminum arsenide has a lattice constant of A aluminum arsenide. This is also few angstroms. For example, this can be say this can be say 5 angstrom, okay, this can be 5 angstrom. I am just giving an example, I do not recall the exact value, but it can be 5 angstrom. This can be say 4.5 angstrom or 4.0 angstrom, for example. Now what will be the lattice constant of aluminum gallium arsenide, which has say X aluminum and 1 minus X gallium? It will be somewhere in between, right? It will be somewhere in between, because of course it has to be in somewhere in between. So this is an alloy, right? It has to be somewhere in between. So essentially Vegar's law says that you can do a linear interpolation, which means the lattice constant of this A aluminum gallium arsenide X 1 minus X will be equal to X times the lattice constant of aluminum arsenide plus 1 minus X times the lattice constant of gallium arsenide. Same thing can be done, for example, with effective mass. Maybe if you have an effective mass of aluminum gallium arsenide X 1 minus X, it will be X times the effective mass of aluminum arsenide plus 1 minus X times the effective mass of gallium arsenide. So it is a linear interpolation, okay. So essentially if I am plotting the lattice constant here, and if I am plotting X here, that is the fraction, so X equal to 0, this point corresponds to 0 point corresponds to purely gallium arsenide, and X equal to 1, that point corresponds to purely aluminum arsenide, right. So your lattice constant will probably go from say 5 angstrom here to say maybe this is 4 angstrom here. I am just giving an example, this may not be 5 and 4, this will be something else, but this is a constant number, by the way, it cannot be arbitrary, so that is known. So it will basically go as like this, a linear plot. So at any point here, if you have X equal to 0.4, X equal to 0.5, 0.6 and so on, you can go here and look what is the value here, okay, and that has a huge implication, by the way, this lattice constant, okay. So similarly for effective mass, so we can do it to a large extent. So essentially it is a linear extrapolation between this, and that is what Vegar's law says. So it is very easy, Vegar's law is very easy. However, your band gap typically will not follow a direct linear relation. A band gap, if you remember in the plot that I had drawn a few slides back, this is the band gap, I did not draw it very linearly. A linear plot would have been like this, right, but it will slightly be bent sometimes. In aluminum gallium arsenide it may not be so much bent, but in things like aluminum gallium nitride for example, there is a lot of bending, okay, lot of bending, huge number. So for example, I take a different material, for example I take aluminum X gallium 1 minus X nitride, this is AlGaN, aluminum gallium nitride, and the band gap of gallium nitride is 3.4 eV. This is a wide band gap material, very wide band gap, and you will be surprised actually if the band gap of aluminum nitride is even much larger. This is around 6.1 electron volt. This is almost like insulator. Yeah, it is insulator you can say, but you can actually dope aluminum nitride N type, and that's why you sort of call it. You can also mildly dope it P type, but you can dope it N type definitely, and so you can call it semiconductor because you are able to tune the conductivity. Okay. So, you know you have a band gap of aluminum nitride this and band gap of gallium nitride is this. So, a band gap of aluminum gallium nitride has to be between this, but it so turns out that it will not be linear. So, what I mean to say is that if I plot band gap here and if I plot x here, so x equal to 0 will correspond to gallium nitride and x equal to 1 will correspond to aluminum nitride. So, the band gap of gallium nitride is 3.4 eV, okay, and the band gap of aluminum nitride is 6.1 eV. Okay. It will not go linearly like this, that is not going to happen. Okay. So, the Vegar's law actually matlab you have to modify the Vegar's law. It will go something like this, oh sorry, okay, it will go something like this. There is a curve here, and that is called the bowing, bow, it is like a bow, right, it is a bowing and there is a bowing parameter, that is why. So, the band gap, and this is true for many compound semiconductor by the way, I am just giving an example of aluminum gallium nitride, but band gap typically has something called bowing parameter. So, what happens is that the band gap of aluminum gallium 1 minus X nitride will be X times the band gap of aluminum nitride, you are right, plus 1 minus X times the band gap of gallium nitride, but there is a bowing parameter. Now, if this is the equation, then you will get something like this, okay, a straight line. There is a bowing parameter here. So, essentially what will happen is that you have to plus some bowing parameter b x into 1 minus x, that gives a non-linearity. This b is called the bowing parameter, okay. And this b is experimentally determined, you cannot do otherwise, you just experimentally determine. You grow aluminum gallium nitride of different composition 10%, 20, 40, 50, 60, and you measure them, the band gap experimentally, optical, whatever, and then you have this you can do this experimental data fitting, you know, like this, and then you do this plot and you get this bowing parameter experimentally. Okay. So, this x into x minus 1 minus x bowing parameter comes here. So, this is called bowing parameter, and this is important in many compound semiconductor, band gap, in GaN, in gas, and so on. This bowing parameter comes. Okay. So, that is Vegar's law. Okay. So, if you do not know the values of something, you can always use Vegar's law. Okay. Now, one of the unique things that compound semiconductor allows, which silicon cannot do, is doing something called heterostructures. Okay. Epitaxy will come within the heterostructure only. Heterostructure, it means there are two dissimilar materials that you are combining. So, suppose you have a layer of gallium arsenide. When I say layer, I am talking about a bulk material, it is not a single atomic layer, it is a thick crystal, maybe it is a wafer. Okay. It can be few hundred micron, few hundred nanometer thick, it is gallium arsenide. Okay. On top of that, you can make an aluminum arsenide, you can grow, actually that is called epitaxy, I will come to that. You can make this structure, okay, or even you can make a structure, it is up to you. You can make, but it is not always random, okay. You can make aluminum gallium arsenide, and maybe this is 25%, this is 75%, whatever, right, anything. So, aluminum gallium arsenide you made. Maybe on top of that, you want to make an indium gallium phosphide, maybe indium 40%, gallium 70%, and so on, right. You can make these structures. So, if I look at the band diagram along this direction, you have, you know, gallium arsenide which has a band gap of 1.4 eV. Then you have aluminum gallium arsenide whose band gap will be slightly more than gallium arsenide because its aluminum arsenide is 2.2. So, this will be slightly larger band gap like this, right. Then indium gallium phosphide might have a slightly smaller band gap, maybe even slightly small big. You can tune, of course, depends on indium. So you see your band diagram actually changing. So you can have different kinds of band diagram like this, right? Different band diagrams can be done, sorry, you know, different band diagrams can be done, depends on the, this is conduction band, for example, this is valence band. This kind of things are not possible with silicon, okay? These kind of things are not possible with silicon. And heterostructures is basically the structure of these dissimilar materials that you are piling up, that you are actually growing on stack on top of another. This is heterostructure, and you can make a variety of devices. Your semiconductor laser is based on similar heterostructures, not exactly this heterostructure, sort of heterostructure, okay? Your white light LED, your RF transistors, many of these devices that you are looking at in your real time, your mid-IR detectors, your 1.55 micron lasers and detectors that you are using for optical fiber communication, all these are actually made on heterostructures. They are used on heterostructures, white LEDs and all, okay? They are all using heterostructures, different kinds of heterostructures. These are basically stacks or structures of dissimilar material. Of course, there are many rules that you have to follow. You cannot physically, practically speaking, you cannot randomly grow or get materials on top of the another material just like that, okay? These are called heterostructures, by the way, so remember that, right? So if I have a material of gallium arsenide, I cannot arbitrarily put gallium nitride here, that will not work. What do I mean by not work? When I say it will not work, it means you cannot deposit gallium nitride on gallium arsenide such that both of these are crystalline. You see the semiconductor band diagram, semiconductor band structure, semiconductor band gap, and all the device physics, your drift, diffusion, scattering, everything is dependent on band gap, band structure, and everything comes from periodic potential. If you recall, periodic potential from very first lectures, K space, EK diagram, and this needs a crystalline material. If you do not have a crystalline material, if you have a polycrystalline or an amorphous material, you do not have a periodic potential, you cannot define a band gap, all the analysis will break down, okay? So for a device to work, you need everything crystalline. When I say crystalline, you understand what is crystalline, right? You have the order, the long range order, your atoms are arranged in a definite fashion in all, for infinite long, okay? No matter where you look, you will always get the same arrangement of atoms, the same spacing of atoms, they are not oriented grains there, okay? It is repetitive, the lattice is repetitive and it is a crystal structure, okay? So it is impossible to get gallium nitride which is crystalline on top of gallium arsenide just by depositing gallium nitride on gallium arsenide, okay? So you cannot arbitrarily have materials. You can have gallium nitride, for example, on top of aluminum gallium nitride. So you see a trend, you need to grow it on the same family of materials, okay? The family of materials has to be same. Even then there are some very important conditions and boundaries conditions and stringent criteria. Even when you grow gallium nitride on aluminum gallium nitride, or you grow aluminum gallium arsenide on gallium arsenide, there are rules that you have to follow, okay? Or any heterostructure for that matter. The one thing is that it has to be within the same family of materials. Now growing dissimilar family of materials is possible, but that is special in some cases only. You cannot grow gallium arsenide on gallium nitride, for example, and all these things, right? And so the thing, and this growth, these materials that you are depositing, this process is called epitaxy. I will come to that quickly, okay? And epitaxy is there, and essentially your heterostructure devices performance and everything depends on whether you are able to grow or deposit this material, whatever material, as per your desire, as per how you have planned. That is why heterostructure is also about material science as much as about devices. If you do not have a materials understanding to a basic extent, you will not be able to design devices, because I might arbitrarily say, oh, you know what, I will put gallium nitride on top of aluminum phosphide, on top of silicon, on top of some random thing like indium antimonide. This kind of structure cannot physically exist. I mean, they can exist, but it will be amorphous. You cannot have this crystalline, okay? It cannot be crystalline, okay? So you need to have a basic materials understanding to allow you to think as to what kind of heterostructure and what kind of stacks are possible, so that you can design and come up with device ideas, new type of device ideas. Okay, you cannot arbitrarily do this. Okay, that's because it's limited by epitaxy. So now I hope you understand what is heterostructure. Heterostructure essentially is, you have stacking of different materials. It can be two stack, it can be 3, it can be multi, it can be 100, who cares, it's heterostructure. Okay, there are different kinds of heterostructure, by the way the band gaps are aligned, it will come in sometime later. But here I am talking about epitaxy. Epitaxy is basically, you have to, when you want to grow a material on top of another material, say you want to grow aluminum gallium arsenide, and this can be say 40, 60, on top of, you want to grow on top of gallium arsenide. So gallium arsenide wafers are available, you can buy gallium arsenide wafers commercially. Okay, so you buy gallium arsenide wafer and you want to deposit aluminum gallium arsenide crystalline. That is a very advanced, sophisticated, costly, expensive and time consuming process actually. Okay, it's not very easy. You have to do epitaxy for that. What is epitaxy? Epitaxy is essentially the process, the physics or the material science of growing a material, for example this material, on top of another material, such that this material, the crystal structure of this aluminum gallium arsenide mimics the crystal structure of the layer below, of the substrate below. So aluminum gallium arsenide cannot have an arbitrary crystal structure, it has to mimic the crystal structure of the material below. That's called epitaxy, and typically it is done by a couple of techniques in which you can deposit one layer by one layer of aluminum gallium arsenide, one layer, the next layer, the next layer. Of course they have a vertical, strong vertical bonding. These are not like 2D materials where the vertical bonding is weak. These are strong bonded materials, and you will have grow them layer by layer. You grow them layer by layer, which means you need to have a precision. You have, when you deposit the material, you have to deposit with a precision of one atomic layer, which is very insane, right? At the precision of one atomic layer you have to deposit this material in such a way that the material that is growing or depositing should be mimicking the crystal structure of the material below, which means if gallium arsenide has a lattice constant of whatever the lattice constant, aluminum gallium arsenide might have a smaller lattice constant, slightly smaller lattice constant. This spacing might be slightly smaller than this. This is called lattice mismatch. When you grow aluminum arsenide on top of gallium arsenide, gallium arsenide on top of gallium arsenide, right, this is gallium arsenide for example, then you have a slight difference in the lattice, it's called lattice mismatch. Aluminum gallium arsenide and gallium arsenide have very negligible lattice mismatch, they are almost lattice matched. So that is not a good example. Okay, they are called lattice matched, as in like aluminum gallium arsenide and gallium arsenide have almost the same lattice constant, so they are called almost lattice matched. Let's take an example of something else, say aluminum gallium nitride and gallium nitride. Okay, so if this is gallium nitride and this is aluminum gallium nitride, it has a smaller lattice constant than gallium nitride. When I say you have to do epitaxy, you want to actually mimic, you want AlGaN, this layer, to mimic the crystal structure below, which means when you grow one on top of the another, this lattice constant that you have here has to mimic or match the lattice constant here, which means this atom and this atom will be pulled apart little bit so that they can be one on top of them, right? This is called, there is a strain that is developing, a strain or a stress is developing in the aluminum gallium nitride layer, because the spacing here is slightly lower and the spacing here is slightly bigger. When you are growing one layer of aluminum gallium nitride on top of gallium nitride, this lattice spacing has to match this lattice spacing. So matlab you are pulling this GaN will basically pull this atom slightly away so that the spacing increases and you are able to deposit them one on one. This is called strain aluminum gallium nitride. But if you keep growing this aluminum gallium nitride strain on top of this will become very strained and stressed, so the energy will increase. Eventually it will try to relax. If you grow sufficiently thick AlGaN, it will try to relax because you are straining it, no? you are straining, you have this is epitaxy, and of course and you have to make sure that this is crystalline, that is why it is very important. You have this for example, that is the gallium nitride spacing I am talking about, and aluminum nitride spacing is suppose this like that, right. So this has to strain so that this can be mimicked, this can form one on one, the bonding can be formed, right. This can form a bonding here, right. You have to, it is very difficult actually, that you have to strain up this aluminum gallium nitride layer on top gets strained, but it can only accommodate the strain up to some time. After a few layers or few thickness, this aluminum nitride will gallium nitride will have so much of strain energy that it will relax. Once it relax, it will go back to its original it will go back to its original spacing. Okay. Once it is strained, when it is strained to gallium nitride. So what will happen is that you will have gallium nitride like this. Okay. Your aluminum gallium nitride also is one on one you will have, but it is highly strained, this layer is highly strained because that is not its natural spacing. If you grow thick, sufficiently thick, it will basically relax, it will basically give away, and then it will come back to its original position. Okay. It will come back to its original position like this smaller spacing. So when the top layer is strained, you call it, that layer you call it pseudomorphic. Okay, pseudomorphic. You can have this indium gallium arsenide on gallium phosphide and other things which are, you can have certain things which are pseudomorphic, and if it is relaxed, that means it has gotten enough thickness and so the material is now unable to get strained to the layer below, it will relax, it is called metamorphic. Okay. Even otherwise when it relaxes, it does not mean that the crystal structure is violated, it has just relaxed, everything will mimic the structure, it is growing crystalline only. Okay, it is growing crystalline only, and that is why that is called epitaxy. You have to, and we do not use the term deposit so much, we call it epitaxy or growth, you can call it growth. Okay, it is a terminology difference, but it is okay, or growth. So you have a substrate, you have a background layer, essentially it is called substrate on which you are doing this. Here you are using GaN for example. Okay. Similarly you can have gallium phosphide or whatever substrate, on top of that you might be growing indium gallium arsenide or indium gallium phosphide and so on. This epitaxy or the growth will ensure that you are growing crystalline material, and two important techniques are MBE called molecular beam epitaxy and MOCVD, which is metal organic chemical vapor deposition. These are techniques that are used to grow these materials layer by layer in a crystalline fashion. These are very advanced and sophisticated techniques that have precision of one atomic layer. You can do one atomic layer by one atomic layer deposition, and that is why you can essentially change the structure very abruptly from one layer to another layer, and you can get these band diagrams which are unique, and this kind of enables the band diagrams and band structures which are not possible otherwise, that allows you to have different functionalities. Okay, that is what is we should remember. So this MBE and MOCVD are techniques that can do this epitaxy and crystalline growth. It can eventually be pseudomorphic or it can be metamorphic, and these are dependent on the lattice mismatch. What is the lattice mismatch? For example, if one layer has a lattice constant of I am talking about just an example, if the bottom layer has a lattice constant of 5 angstrom and the top layer that you are growing has a lattice constant of 4.9 angstrom, then it is a very small lattice mismatch, you would be able to grow little thicker until the material relaxes. If on the other hand the lattice constant is 4 angstrom on top and 5 angstrom on bottom, then you will be getting so much of strain that in a few layers it will basically relax. Okay. So lattice mismatch, the degree, the percentage of lattice mismatch dictates how much you can grow pseudomorphic or strain. Okay. Even then, either it's pseudomorphic or metamorphic, you will be able to grow crystalline materials, and only when you grow crystalline materials you will be able to get this heterostructure of gallium arsenide, aluminum gallium arsenide and so on. So these structures you cannot arbitrarily assume, and then you can grow and you can do it. These have a material limitations, and these have a from a materials point of view you should be able to justify whether such a structure is possible. Okay. Once such a structure is possible, then you can do fanciful things. Okay. Once such a structure is possible, then you can do many things. For example, you might take a layer of say for example indium arsenide has a lower band gap than gallium arsenide. Okay. So if you take indium gallium arsenide you, so whatever x 1 minus x, the band gap will be lower than gallium arsenide. Okay. So, suppose I have a layer of gallium arsenide on top of say indium gallium arsenide, thin layer, and then there is also a gallium arsenide layer below. Okay. And what are the thicknesses of these epitaxial layers? They can be as low as 1 to 2 nanometer to 2 nanometer, sorry, not micron. Even you can grow 1 nanometer using MBE, 1 to 2 nanometer, of course you can grow 1 nanometer using MBE or even sub 1 nanometer by the way, and you can be few tens of nanometer, 20, 30 nanometer, you can grow few hundreds of nanometer, 100 to 500 nanometer, you can even grow micron. Anyways, typically this can be thin. So, when I am talking about this structure, suppose I am talking about a very small structure, suppose this is only 5 nanometer and this is suppose 50 nanometer, this is substrates, it can be much thicker also, does not matter. Now, because indium gallium arsenide has a smaller band gap than gallium arsenide. So, if I draw the band diagram, it will look like gallium arsenide is this, say 1.4 eV, there is also gallium arsenide on the other side 1.4 eV. In between I have indium arsenide, this is by the way conduction band, conduction band, conduction band, this is valence band, valence band, valence band. In between you have indium and gallium arsenide whose band gap is small. So, the band gap here might be say 1 eV. If you join them together, you will have a band diagram like this. This is conduction band, this is valence band. This is conduction band, this is valence band, this is 1.4 eV of gallium arsenide, this is again 1.4 eV of gallium arsenide. In between you have say 1 eV of indium gallium arsenide. You see this structure where you have a, this is conduction band. So, this is a potential, you have a potential profile like this, you have a potential profile like this. Do you know what it looks like? It looks like a quantum well. You have probably read about your quantum confinement, you have read about in your high school physics, in your 10+2 physics, you might have read about particle in a box in your physics, in a particle in a box. This is the practical realization of a particle in a box. If you put an electron here, it is like a box, there is a potential profile on either side that will not allow the electron to escape. It is not infinitely high potential, that is okay, but it will not be able to escape outside, right, or a hole here is confined here, right. An electron in a hole will not be able to escape outside. It is like a well, it is a particle in a box, a quantum well, and these are used not only in optical devices like LEDs and laser diodes, these are also used in transistors, high speed transistors, we use them. So, particle in a box that you had learned in your high school or 10+2 physics can be practically realized in heterostructure only. Okay. So, this heterostructure allows you to get that particle in a box sort of a configuration. Okay. So, this is a beautiful thing actually. So, let us end the class here today. We have had sufficient orientation and knowledge of compound semiconductor. So, we have talked about Vegard's law, epitaxy, why you need epitaxy, that you have to mimic the crystal structure below. Lattice mismatch is a big issue, and you have to make sure that you cannot arbitrarily come up with device ideas by putting any arbitrary material on any arbitrary substrate. It has to follow lattice mismatch, and this crystalline, it has to be crystalline. So, you have to do epitaxy, and the material science will put a restriction on what kind of things you can do. Once you can do those things, you can also apply Vegard's law to extrapolate the alloy composition and other things. The band gap of course does not follow the Vegard's law exactly, you need to have a nonlinear factor, that is the Boeing parameter. And I told you things like particle in a box or quantum well can be realized in a proper heterostructure. Okay, it can be realized in a proper heterostructure, and your material science will always dictate what is the realistic estimate of your device you are making. You know, it is not like just silicon, that you have a silicon material and you can do things. Doping is another thing by the way that I did not discuss here. So, in the next class I will tell you about the different kinds of heterostructures. I told you about the different materials, arsenide, phosphide, antimonide, oxide, nitride. I am talking about the different classes of heterostructure. When you have two structures, heterostructures, how do they align in their band diagram? That is what I am talking about. Okay. We will talk about heterostructure alignments, and we will talk about heterostructure band diagrams in the next class. Okay. And we will start also talking about devices from thereafter. Okay. So, thanks for your time, we will meet you soon.